In the summer of 1758, Charles Messier was frustrated. The 28-year-old French astronomer had taken up comet hunting as something of a vocation, and he hoped to be the first person to observe the return of Halley's predicted comet. The problem was that as he scanned the night sky from the roof of the Hôtel de Cluny in Paris, he kept getting distracted. Messier had come to his self-appointed mission by way of the French Navy, as he had made something of a name for himself as a reliable observer, having observed the Mercury transit of 1753 while in the employ of Joseph Nicolas Delisle. As he searched the sky for Halley's comet, as well as any others he might come across, he kept running into these strange and frustrating objects that looked like they might be comets, but actually weren't. When comet hunting, as we have seen, the idea is to look for things that resolved into fuzzy-looking objects when viewed through a telescope, which, in Messier's case, was a very serviceable 4-inch refractor set up on the hotel's roof. If one found such a fuzzy object, one would then measure its position with respect to the other objects around it and then return to it every few nights to see if it moved. This is how Herschel had discovered Uranus. However, in 1758, there was a complication. As Messier scanned the sky, he kept coming across these fuzzy objects that looked like comets, but that when observed on later dates, showed no signs of having shifted positions. Due to their fuzzy and nebulous nature when viewed through the telescope, Messier called them nebulae, and soon came to hate them. The problem was that he kept bumping into them, and so, not having good records of where they were, he would waste precious observing time unnecessarily finding them over and over, until he hit on an idea. Why not make a list of the nebulae he came across, so that when he encountered something fuzzy during a comet hunting run, he could check it against his list and discount it if it were already there. With his colleague, Pierre Michon, he would compile the first catalogue of nebulae, the first edition of which would be published in 1774 and contained some 45 objects. By that date, while he had failed to be the first to cite the return of Halley's comet, he had discovered 8 new comets and had been elected to both the French Academy of Sciences as well as the Royal Society. And before his death, he would add 5 more comets to that list, permanently cementing his name among the pantheon of great astronomical discoverers. More importantly for posterity, however, he began to publish an updated list of nebular objects every few years after 1774, with the number of entries eventually growing to some 110 Messier objects as they are known today. The final version would be published in 1784 and would prove to be extremely influential in guiding the observation program and scientific career of the recently installed astronomer to the court of George III near Windsor Castle. The Messier Catalog, as it is now known, marks an unknown and unintentional shift in astronomy from being almost exclusively interested in the motions of the objects of the solar system to a recognition that there were things beyond the boundaries of that which orbited the sun. While Messier may have viewed these nebulae as nuisances, one astronomer would see them as the gateway into the wider universe, and thus single-handedly move astronomy out of the shallow end of the celestial pool into the deep waters of a cosmos unimaginably more interesting and diverse than anyone had ever considered. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 29.2, Supplemental, The Herschel Dynasty. As we begin this second episode on the scientific biography of William Herschel and his extended family, let me make a few introductory comments. Up to this point, the narrative has been fairly single-tracked. We've followed the life of William Herschel from his humble origins in the German province of Hanover, through a musical career in England that led him to the quiet but well-to-do resort town of Bath, where he took up what began as a hobby but became something of an obsession: astronomy. As a part of this, we were able to thread together the intertwining activities of his musical career, his growing proficiency in making astronomical instruments, his emerging skill in applying the processes and techniques of natural history to a systematic study of classes of astronomical objects, and the somewhat confusing comings and goings of his brothers and sisters. This, of course, resulted in a rich but understandable tapestry of things that could be examined in a mostly linear fashion. Going forward, though, that's going to become much more difficult to do. After being hired as George III's personal court astronomer, things get a lot more complicated and multi-tracked for a while. As such, we'll find ourselves running through a topic only to backtrack to pick up a thread we had to neglect earlier. I'll do my best to keep it all straight, but if it becomes a bit confusing at times, take that confusion as a recognition of the extraordinary breadth and depth of the Herschel scientific enterprise. Second, for the purposes of our story, I'm not sure that flying low and slow, as it were, is necessarily in our best interest in many cases here. William's work is legion, and to try and make comments on each and every part of it would be to risk losing the forest for the trees. As such, I really want to focus on the big picture here rather than getting into all of the details and minutiae of his ideas and thoughts. In other words, to use our aircraft analogy, I'd like to climb to get a bit of altitude so that we can more clearly see a big picture of all of the things that are going on, as I think there's a great deal to be learned from having that sort of a perspective. Finally, as I've done the research for this and some of the other episodes to come, I've really become convinced that in the life and work of William Herschel, astronomy experiences a fundamental paradigm shift that will become the focus of the second half of this Finding Our Place series. As I wrote the closing episodes devoted to both the more specific Copernican and then broader scientific revolutions, I kept wondering how I was going to transition from that period to the discoveries that would usher in our modern view of an expanding universe filled with innumerable galaxies made of trillions of individual stars. The question I kept asking was, how did we get from a focus on the arrangement and motion of the planets through space, that thing which had occupied the minds and curiosities of astronomers from the time of the ancients up through Edmund Halley, to an understanding of not just our place in a galaxy of stars, but in a universe filled with galaxies? What I've learned in my reading is that William Herschel, as much as any one person can be, is that bridge. It is his work, but even more, it is his ideas that propel astronomy out of the solar system. An irony given that the thing that he is best known for doing is doubling the size of our solar neighborhood with his discovery of Uranus. It is my hope that by the end of this episode, you'll better understand how that transition occurred. Alright, so let's get to it then. When, in 1782, Herschel is hired by the British Royal House, he has made available to him an old hunting lodge not far from Windsor Castle. While I don't want to get into the various geographic minutiae of the region, the place wasn't too far from the crossroads stop on the road from London to Bath, known as Slough, that would factor so prominently in Herschel's career as time went on. By the way, apparently the place may have been called Slough because that's where the carts and such that would travel down the road would have to slow down. While the grounds were certainly adequate for the enterprise about to be undertaken, especially in terms of the workshop space the former stables and servants' quarters would afford at the lodge, the place had been unused for some time and was in quite the state of disrepair. Caroline would complain in her letters home that the roof was leaky and the grounds were quite overgrown. Nevertheless, William, with Caroline and Alexander's help, along with the resources provided from the nearby royal residence, was able to get things in some sort of a working order fairly quickly. The first thing we should discuss as part of this, probably, is William's work in instrument design and making. During his last year in Bath, he had begun working on designing telescopes with both bigger mirrors and longer focal lengths. He'd gone through this whole series of things where he had tried to make bigger and bigger mirrors, culminating in an effort to try to cast a mirror that was a piece of metal that was 3 feet across. Unfortunately, that effort had failed, but he had learned tremendously from it. And as you'll recall from our last episode, each of these expansions led to different improvements in a telescope's functionality. And by the way, one thing I neglected to mention in my digression regarding telescopes in that episode is a resource that I found very helpful when teaching this material, so we'll have a little digression here in this episode. The folks at AmazingSpace.org, NASA's education outreach initiative associated with the various space telescope programs, have put together a really fantastic website on the history of the development of the telescope called Telescopes from the Ground Up. If you want to learn more about the history of telescopes, as well as some of the physical principles about how they work, this is really a great resource. We'll post a link to the site at the podcast's website, thescientificodyssey.typepad.com, and to our Facebook for those who are interested in learning more. But if some of the stuff that we talk about with telescopes seems a little confusing, that's a great place to go to sort of get a better sense of how telescopes work and how the lenses and mirrors combine to produce the images we're talking about. Okay, so when William was in the process of discovering Uranus, he was also building his first 20-foot telescope that had about a 12-inch mirror and planning instruments of larger size, including something that might be 40 feet long that would have a mirror 4 times that size of the 12-inch mirror, something 4 feet across. While he would finish the 20-foot scope, he would find it very difficult to use in the confined space in Bath, and so most of his double star work was done on his more modest but optically exceptional 7-foot scope that we discussed last time. However, with the move, there was a chance to design a new mounting system for the 20-foot telescope that would allow it and its successors to become substantially more functional. As an important note, this would be a problem here that would plague Herschel his entire life. While he could build telescopes of really remarkable size, the problem was usually one of how to actually point the telescope at things in the sky. As his telescopes got bigger and bigger, they became more and more unwieldy, so he had to come up with new ways to point them, especially in an age before widespread mechanization. The other issue associated with this was the fact that Herschel had taken a pretty significant pay cut to join the royal court. His stipend there was some £200 a year, which isn't too shabby by any count at the time, but it was actually only half of what he had been making as a musician and an orchestra director in Bath. Now, once he realized this, George III was, well, a little embarrassed as to the amount, as it made him look a bit miserly towards the man who had proposed naming a planet after him. As a way to help offset this loss, the king encouraged William to set up a telescope-making business that would sell very high-quality instruments to any interested buyers. Of course, the first on that list was the king himself, who ordered 5 10-foot scopes for various observatories under his auspices and to be used as gifts. Once word of this got out, customers both domestic and foreign were soon lining up to get their hands on one of the fine Herschel instruments. According to one source that I read, the Herschels, William and Alexander working together, constructed over 1,000 instruments, most of which were sold to others rather than being used by William in his work. If this estimate is true, it would seem that for the period of the late 18th and early 19th centuries, the Herschels were responsible for most of the telescopes being used in Europe as means of astronomical research. Aside from the 40-foot behemoth he would construct for his own use, the largest and most functional of these telescopes from a research standpoint was a 25-foot instrument William would make for the King of Spain. Completed in 1801, it was likely the best telescope in all of Europe until it was destroyed in 1808 as part of the Napoleonic invasions of that country. While various optical elements have been salvaged from that instrument, the tube and the scaffolding used to support it were lost. Recently, a reconstruction of the telescope using the original mirrors has been created. Now, when you bought a telescope from the Herschels, you usually bought something of a kit that you had to assemble. In that kit was an innovation that made such instruments really, really useful. Most of the telescopes, at least those of a larger size, came with two sets of mirrors. As the mirrors were made of a metal alloy, over the course of time, that alloy would tarnish, especially in humid environments. As such, they would have to be regularly removed and repolished. Having two sets of mirrors that could easily be swapped out allowed for the telescope to remain in use rather than being down for the time it took to get the mirror back up to snuff. This helped the Herschels corner the telescope market in their time. As previously mentioned, not only did William corner the market on telescope manufacture, he also devised new ways to efficiently make observations. As his telescopes grew larger and larger, they were harder and harder to move. This was especially true when he replaced his smaller 12-inch aperture, 20-foot-long focal length telescope with a similar 20-foot-long telescope that had an 18-inch aperture. The solution Herschel arrived at was to point the telescope due south and then let the sky do the turning. He then used two workmen to use a system of ropes and pulleys to move the telescope right and left so that he could follow an object some 10 or so degrees across the southern sky as needed to make the appropriate observations. The telescope could also be raised and lowered as needed along with the scaffolding, and there was actually an observing platform for Herschel to stand on. The only drawback to this was that the scaffolding only allowed the telescope to be raised so high, and thus observing was limited only to a certain band of the celestial sphere. While Herschel had plans to construct a different sort of scaffolding in order to allow observations of the circumpolar region, he actually never really got around to it. What turned out to be the bigger issue to solve, however, had to do with the recording of data. When William had been observing fairly bright objects, the use of an artificial light such as a candle or a lamp hadn't been all that much of an issue. While the light did cause the pupil of the eye to contract, the diminished sensitivity to light really wasn't all that big of a deal. However, once William began to observe fainter and more diffuse objects, looking away from the lens and at a flame would render his eyes unable to see the target through the lens for several additional minutes. He originally solved this by having Carolyn on the platform to record his measurements, but that proved to be very unworkable. He next built her a bit of a hut and desk at the base of the telescope, but again, as the temperature dropped, this too was less than satisfactory. Soon, the two worked out a system where she would be in the manor house near a fire with all of her needed resources and sources at hand, which, by the way, the most important of this was actually Flamsteed's catalog, which we discussed in an earlier episode. When William had a measurement, he would signal her through a pulled cord, and she would open the window, wherein he would call out whatever numbers she needed to record, and she could relay back to him any relevant information he might need as to what star might be the next thing that they wanted to observe and how much they needed to shift things, whatever the case may be. In this fashion, the two Herschels, brother and sister, would undertake a number of systematic observing projects that sought to resolve a number of questions William was now considering. So, with all these technological advances, what was it that William really wanted to do? What was his observational program, to put it in sort of modern parlance? To begin with, as he was getting things set up at the new hunting lodge, which by the way was known as Dashet, he continued to use the 7-foot reflector to make observations for the double star catalog he'd been working on for some time. This work was complicated by the fact that his paying gig actually had a few responsibilities of its own. Unlike the astronomer Royal, whose job was to do observing, William had been hired to entertain the royal family and its guests. So instead of having to take on musical students, he often had to schlep his 7-foot scope over to Windsor Castle for a night stargazing party before traipsing back home with the thing in order to do some observing through the long night. When he finally got that 20-foot telescope up and running, it would be the king and his family who would have to come to dash it, as the whole thing was just too big to be transported. Due to the king's genuine interest in and enjoyment of astronomy, it was not uncommon for him to just drop in with only a squire or two for company. Can you imagine being a servant and answering the door at the Herschel household? "Hello, Mr. Herschel. His Majesty is here to look through your telescope, sir." Fortunately, or perhaps unfortunately, given the fact that the king actually had the means to do something about it, the couple, Herschel and his sister, only had to receive royal guests on nights when the sky was clear enough for viewing, and so they were spared the embarrassment of having to explain their leaky roof. As all of this was going on, William began to give thought to more and more questions regarding what sorts of information he could glean from his growing compendium of observations. And it's here that we really see the scope and creativity of his mind, because these questions are really very breathtaking in nature. So the first thing he wanted to think about and wanted to know about was whether the sun was moving through space among the other stars. The next question that he sort of wanted to consider is, he wondered if there were regular patterns to the variations in the brightness of some stars, most notably Algol, that he could sort of characterize. And then finally, he really was curious about what kind of spectrum of light was created by the stars, and how did all of that compare to what you saw through a rainbow. And all of those are really interesting sorts of things. That last question, by the way, would lead to a few other things, like him asking whether light actually traveled through space at the same speed. And so, the thing that's really fascinating about this is it's just you really see his mind beginning to range broadly around in the subject of astronomy and ask really interesting physical questions. And you should be warned here, because these are just the beginning of where he's going to go. So let's take a look at that first question. Does the sun move through space? On the surface of it, from our perspective today, this seems like maybe kind of an interesting question, but not anything really, what you might call earth-shattering. But let's take a step back and recognize it for what it really would have been at its time. Less than 100 years before Herschel's working, one might argue that the majority of astronomers and natural philosophers outside of England certainly, and maybe inside England as well, believed that the Earth was the stationary center of the entire universe. While Newton's work, along with the attendant evidence gathered by Halley and others, had disproved that model of the cosmos, it was still broadly held that if the Earth was not the center of the universe, the sun it circled had to have been. So for William to ask if the sun moved among the other stars, that's a really revolutionary idea for his time. And while he wasn't the only one asking it, he felt like he might have the data to actually answer the question. And by the way, it is here that we begin to see that transition that I mentioned in the introduction. Herschel is really starting to think outside of the solar system. He is, of course, building on the work of Halley's observation of proper motion of stars, but he's adding the possibility that the motion might be due as much to the sun's travel as it is to that of those individual stars. The idea, something that had been around for a little while, was to see if there was a pattern to the proper motion of the stars that could be attributed to the sun's motion. A good way to think of this is this. If you were walking through a forest, even though the trees don't actually move, some of them will pass by on your left while others will pass by on your right. Moreover, as you approach, say, a line of trees that was perpendicular to your motion, the ones that sort of are on the left of your line of travel will look like they're actually traveling left away from you, while the ones on your right will look like they're traveling to the right away from you. By using these two things, you can get a pretty good sense of what direction you're traveling through the trees, even if you don't have any other external reference points. And this is exactly what Herschel does with the proper motions of the stars, many of which had been measured since Halley's original discovery. And what he came to the conclusion of was that the sun was moving towards a specific star in the constellation of Hercules. Now, while there was a bit of luck involved in his analysis, it turns out that he was almost exactly right. And it's really a remarkable piece of work and insight. Just truly massively creative in him taking data that already existed and reimagining it to come to a result that no one else had come up with. So in the case of the second question, in what was sometimes known as the question of Algol and variable stars, William was pulled into a research program that had been started by a colleague from Bath by the name of Pigot, and had been expanded upon by a deaf and mute collaborator of Pigot's by the name of Goodricke. They had observed Algol's brightness dim by a factor of 2 very rapidly, and then return to its original level shortly thereafter. Now what they did was really interesting. They hypothesized that Algol was being eclipsed by a very large planet, and thus the eclipses should occur at regular times. Now it was at this point that Pigot communicated the duo's suspicions to both the Astronomer Royal and Herschel and asked them to help confirm any future observations. They had gathered a lot of data and had a pretty good idea of when these eclipses that they thought were going on should happen. And this led to 2 things. First, the pair found 3 more short period variables as they are known, and thus they established the study of variable stars as a legitimate field of astronomical research. And it also spurred the astronomical community to find better ways to measure and define brightness through something of a comparative scale. For our story, even though William didn't do a whole lot of direct work with this other than to confirm those observations, William realized that he wasn't collecting enough data when he would observe stars. He realized that what he needed to do is not just get positions, but also brightnesses. And so the whole thing caused William to add to his list of measurements to be collected the brightness of the target. And so this resulted in a catalog of brightness for nearly 3,000 stars that would form the foundation of stellar research in the late 19th and early 20th centuries. Without that data, a lot of the really good astronomy that gets done right at the turn of the 20th century wouldn't actually have gotten done. Finally, on the question of stellar spectra, William was pushed by his friends to investigate whether his telescopes could gather enough light from a star to generate a spectrum when that light would shine through a prism, as Newton had done with the sun. William had long been fascinated by the obvious observation that stars had different colors, and so on May 21st of 1783, he used a 10-foot reflector with a really super stable mount to gather light from 2 stars in the constellation of Cephus. Now, the light from the 2 stars, by the way, are Alpha Cephei and Mu Cephei. And what he did is he gathered the light, had it pass through the lens into a prism that he held between the lens and his eye. Now, the Alpha star is much brighter and looks white to the naked eye, while the Mu star is dim and reddish. And what Herschel found was that there were indeed differences in the spectra, with the Alpha star showing something relatively similar to the Sun, while the Mu star only displayed red, orange, and a bit of yellow in its spectrum, but none of the colors like, what we'd think of as green or blue or violet. While he couldn't do much beyond that, as the time of scientific spectroscopy was still a half a century in the future, his observations ushered in the first bits of stellar astrophysics. He would make notes of the spectra of several stars, including the 6 brightest that could be seen from England, and those would become useful again in posterity. As part of this, he also began to wonder why the prism broke up different colors of light in the way that it did. Why was one color bent more or less than the other? Now, Newton had thought that the reason was because the different corpuscles of light had different sizes or densities, but there was another hypothesis that said that the different colors of light, the corpuscles of those, each had slightly different speeds. It was recognized that if this were the case, one might be able to test the idea by observing a rare event of a planet eclipsing a star. If the speed of light for red corpuscles was greater than that for violet corpuscles, the star would appear red at first, and then it would return to its normal color over time. While this is actually a trickier observation than it sounds, due to Herschel's correct assumption that all planets, or at least almost correct assumption that all planets had atmospheres just as the Earth does, it was recognized that the whole process could also be applied to Jupiter's moons coming out from behind the eclipsed planet. And so Herschel made an observation of the moon's coming out of eclipse on October 28th, 1783. And he noted that the moon was reddish at first, and that after a period of about 2 minutes, it had, quote, regained all of its light, end quote. Well, this can be seen as a confirmation of the differing speeds hypothesis. Herschel felt too strongly about the interference of the planet's atmosphere to place much stock in his observation. Soon, however, all of this work was to be eclipsed, and the pun here is, of course, intended, by a side project he had set up for his little sister to work on. And it is here that we really should spend some time on Caroline, as she will turn out to be an astronomer as talented as any in Europe. When she had come over to England, she had hoped to be a musician like her brothers. She was a passable singer, and she had performed several times in Bath and to good reviews. However, when her brother moved to Datchet, there was no more musical work for her to do, and so she was left with little to occupy her time outside of establishing and running the household. Aware of this, William sort of assigned her something of a project to occupy her when he didn't need her as an assistant. What he did is he set up a small telescope mounted so that it could rotate around a vertical spindle. With this, Caroline could set the telescope at any given elevation, say 50 degrees above the horizon, and then rotate it around the sky, thus observing a small strip. She could then change the elevation and repeat the process. Now, it's pretty clear from her writings of during this time that Caroline wasn't exactly enamored of this idea, and she initially seems to have only participated because she'd been instructed to do so by her brother. William had told her to look at anything that caught her eye. Double stars, planets, comets, whatever. And it really wasn't all that interesting work at first, but that changed in late 1782. At the close of that year, she was sweeping across the sky when she came across a nebula that was actually the 27th object in Messier's catalog. This was a new object for William, and so he got pretty excited about it, though once he realized it was already among the list of Messier that William Watson had sent him recently, that, his excitement waned to something closer to just mere appreciation. Sort of oh, that's really kind of cool, but, someone already discovered that, so let's move on. Caroline, though, continued to sweep the sky whenever she had the chance, and she found several more of Messier's nebulae. Then, on February 26, 1783, she came across a nebula that wasn't in the catalog. While it was actually what we now know as M93 in the catalog that Messier provided to the French Academy of Sciences, the list wouldn't be officially published until 1784, and so nobody knew that it was on there. And thus one can say that Caroline independently discovered the object. And on that same sweep, she discovered a second object not in the catalog, and it was there that she was bitten by the bug of discovery. Henceforth, Caroline would be an astronomer in her own right. Using an upgraded version of the spindle telescope, Caroline would go on to discover some 8 comets and write her name into the history books. We do need to dispel one myth, however. As Tony Christie points out in a post to his Renaissance Mathematicus blog, there is an oft-told story that holds Caroline to be the first woman to discover a comet. As Dr. Christie points out, this isn't actually true. The first woman to do that was the wife, Maria, of the German comet hunter Gottfried Kirch, who we've mentioned in our previous episodes on Newton. However, as Gottfried published Maria's discovery under his own name, as he thought no European journal would publish the work of a woman, there is, or was at least, no record of Maria's discovery outside of her husband's notes. While Maria's work is outside the scope of this narrative, it should be noted that she did finally publish several of her own works, most notably on sunspots in German, and upon the death of her husband continued to make significant contributions to the astronomical community, helping in fact run the Prussian Royal Academy's main observatory. So well regarded was she that Tsar Peter the Great even offered her an astronomical position in Russia in 1714, one that unfortunately she turned down. Now, what can be said here is that Caroline is the first woman to publish her discovery under her own name, in this case in the philosophical transactions of the Royal Society. Until she left England following her brother's death in 1822, Caroline had friendly relations with both the Astronomer Royal and the president of the Society, who marveled at her astronomical talent and understood that William probably didn't truly appreciate what he had in his sister. In her lifetime, Caroline would be the person primarily responsible for organizing her brother's observations in a form that would be accessible to other astronomers. Her work on this was eventually published under William's name by the Royal Society, and it became the basis for what would eventually be known as the General Catalogue. When this was expanded upon in the early 20th century by William Draper, it would be renamed the New General Catalogue, and the nearly 3,000 deep sky objects, as they are now known, observed by William and documented by Caroline, would be given NGC numbers that they're still referred to by today. For her work, Caroline would be honored by the Prussian Academy of Sciences with a gold medal. Additionally, she'd be elected an honorary member of the fledgling Royal Astronomical Society, who would also award her a gold medal, something it would not do again for a woman in astronomy until 1996, when Vera Rubin would be so recognized. Without question, Caroline was a brilliant astronomer in her own right, even if she was often treated as little more than an assistant by her brother. When William received his second royal grant for the construction of his monstrous 40-foot telescope, a stipend of £50 per annum was afforded Caroline, making her England's first woman to be paid to do scientific work. She was well respected by the scientific community of London, and when she moved back, in Hanover as well, for her absolutely fanatical devotion to detail and dedication to whatever task she set her mind to. To close this brief section, let me try and give you some insight into that last aspect of her character. As her reputation grew and her cometary discoveries brought her fame, she was asked to check Flamsteed's star catalogue for errors. Considered to be the astronomical Bible in England for over 100 years following its publication by Flamsteed's widow, William and Caroline's work had suggested there might be some discrepancies between the data collected in Volume 2 of the work and the published positions of the stars in Volume 3. Caroline painstakingly went back through the catalog and found and corrected many errors. Moreover, she found that there were instances where Flamsteed had observed an object, but then his widow had not translated that data into the star charts in Volume 3. Her corrections were then incorporated into later editions of the work. As I understand it, no one has since found an error in Caroline's corrections. And she did all of this while she assisted William in his data gathering and conducted a research program of her own. Pretty darn impressive, I'd say. So let's return to the upshot of Caroline's discovery. What William realized was that she had discovered 2 nebulae with a very modest instrument. What this meant was that there were likely many, many more to be found if someone had the instrument and the approach to do so. Hence, he began in 1783 to make a systematic survey of the sky with Caroline as his recording assistant, and he did so to find as many nebulae as he could. As he did this, William began to wonder about the structure and composition of the objects he was observing and whether or not these things changed. Now, I don't think I want to go into all of the details of his thinking here, as those details probably aren't all that relevant to our narrative. Instead, I'd like to focus on 2 aspects of his thoughts in order to get that broader sense of his creativity. The first thing he asked was whether or not the nebulae were made up of gas and or dust, or whether they were conglomerations of stars seen from such a vast distance that they actually just look like fuzzy patches in the sky. In this, he was initially swayed towards the latter position due to being able to resolve some of Messier's objects into collections of stars. Objects that had just been sort of blurry fuzzy patches like M4 and M13 when they were observed with Herschel's large 20-foot reflector, resolved into what we now call globular clusters, which consist of thousands or millions of individual stars. The other thing he became convinced of was that some of the nebulae had changed their shape over time. This was a momentous realization in that it began an intellectual revolution, first in his thinking about the cosmos, and then among his peers after he published a series of 4 profoundly influential papers in the Philosophical Transactions. The upshot of these papers was to overthrow a view of the universe that said that the cosmos was unchanging. Instead, Herschel said, one had to understand that the universe evolved. It changed over time. Star clusters started out in one configuration when they were young, and then, as time progressed, the organization and composition of the cluster would change due to the mutual gravitational attractions of the stars on each other. While he would get some of the details of this wrong, and by wrong I mean really wrong, his idea that the cosmos underwent change can truly be thought of as the birth of modern astronomy. The paradigm that we have today of a universe that began, evolved to its present state, and will continue evolve to a new state can be traced to Herschel's 4 papers published in the Philosophical Transactions. We are, in this sense, without question, more Herschel's heirs than we are Newton's. Newton had believed that the universe was in a steady state through the direct intervention of God, but Herschel convincingly argued that this model was incorrect. In every model related to astronomy, this idea of evolutionary change can now be found. And as a side note here, when I say evolutionary change, what I mean is something different than what is discussed in biology. As the biologist and author Stephen Jay Gould pointed out in an essay, the idea of evolution rightly belongs to astronomy, where gradual change of a single system can be understood to take place. In biology, the idea of evolution as being a process of several discontinuous changes that accumulate to produce diversity is a profoundly different thing, and it is only through a historical accident that the two share the same terminology. This idea of universal evolution would be most influential in prompting Herschel to attempt to use his telescope to make a map of the stars and thus determine both the shape of the galaxy and the sun's place in it. Using a method he called star gauges, he was able to ferret out a distribution of the stars that we see around us. My colleague, Todd Timberlake, has written that these star gauges relied on 2 assumptions, and I'll quote his paper here. First, stars are distributed more or less uniformly within the Milky Way system and are not found beyond the boundaries of that system. Second, the telescope used for the star gauges is capable of resolving all of the stars within the Milky Way system. As Timberlake points out, these assumptions, if they are not true, can distort the model of the Milky Way and give an answer that places the sun at the galaxy's center. What is true, however, is that Herschel was able to correctly deduce that the Milky Way was a stratum, or is, I should say, a stratum of stars. In other words, that most of the stars lie along a plane with finite thickness. A good way to think of this is to sort of think of it as a big disk. While Herschel will begin to realize the limitations of his star gauges late in his life, his work on the structure of the Milky Way would stand well into the 20th century when it would be overturned by the work of Harlow Shapley. Once again here, what's important to see is that Herschel is continuing the dismantling of the old spherical model of things. Stars are no longer contained on or even within a celestial sphere of huge size. What becomes apparent in his work is that such a thing as a celestial sphere is an abstract construct created by our inability to see depth at such vast distances. While useful as a tool for communicating positional information, the celestial sphere was no longer thought to be something real or physical. This, however, left open the question of what nebula were. In order to answer this, William decided he needed an even larger instrument, and so he set out to build a 40-foot reflector with a mirror that would be 4 feet in diameter. Much, much larger than anything that existed anywhere in the world at the time. It was a project that would push the technology of the age and create a breach, at least for a time, between William and his benefactor, the king. The cost of the project was enormous, and as will be the case so often in the future when developing new and untried technologies, there were setbacks and cost overruns. Nevertheless, in 1789, the beast was finished, and almost immediately was used to discover the 6th and 7th moons of Saturn. Herschel would soon turn it towards the nebula he wished to observe, and found to his great surprise that one of them showed a star at the center of a patch of nebulosity. This result caused him to reconsider his hypothesis that all nebulae were comprised of a multitude of stars. It also resulted in his proposal that what was being seen here was a star in the process of formation. While he got the part of the stellar evolutionary cycle associated with these planetary nebulae, as he called them, wrong, his observations were instrumental in supporting the idea that stars are born, live, and die. Unfortunately, the 40-foot telescope never realized its full potential as an instrument. It was so big that it was hard to move easily, and Herschel often found that he could achieve satisfactory results with the 20-foot telescope, and so the 40-foot telescope was kind of left unused quite frequently. The construction of the 40-foot telescope also occurred at a time of great change in Herschel's life, one that would begin the process of taking him away from his astronomical work. In 1787, as the plans for the 40-foot scope were taking place, it was realized that the Dashet facility would no longer be practical for observing. It was too damp, and there were just too many issues with the site, especially as he had to move equipment in and out of it. As such, William began to cast around for a suitable site to move his operation to, and soon decided that the crossroads town of Slough was probably the best place to set up shop. The road would allow him to move large mirrors to and from London with a great deal less trouble, and it would also allow his family to travel between London and Bath, since that was becoming a much more frequent occurrence as Caroline's fame as an astronomer grew, and Alexander would come when the music season was over to help with the telescope manufacturing business. As the move progressed, William came into contact with a woman, Elizabeth Baldwin, who owned a good deal of property in the area. Eventually, he would rent a home from her there, and in doing so would come into the acquaintance of Elizabeth's recently widowed daughter, Mary. William would court her, and after a bit of drama, the two would be wed in 1788. This would cause quite a bit of upheaval in the family as it disrupted that brother-sister relationship between William and Caroline, but in time, as Caroline came to see that Mary was both good for William and kind and generous just in her own right, things settled down quite a bit. This marriage would produce a single son, John, to whom we will return in a moment. In the years following the marriage, William and Caroline would continue their observations, but at a slower and slower pace. In early 1800s, William's scientific interests would branch out a bit, and he would discover infrared light and a really interesting correlation between sunspot numbers and the yields of wheat crops. It'd be something he'd actually get a lot of ridicule for initially, but over time it turns out that his identification of that correlation would actually be upheld. He also speculated on the possibility of life on other worlds, something he thought to be commonplace. He coined the term asteroid and was feted by scientific and world leaders all over Europe. He was, in short, the greatest astronomer of his age, something acknowledged long before his death on the 25th of August, 1822. His epitaph read, "He broke through the barriers of heaven." His legacy, however, would endure quite a bit longer. Born in 1792, William and Mary's son John had what can be thought of as an unsettled childhood. For the early years of his life, his father was frequently away on travel, often accompanied by his mother. When he was old enough to go with them, his life would be marked by sort of a lack of permanence and a sort of always present piece of change in a sense. His schooling was sort of all over the place, though in time he would attend and graduate from Cambridge as the senior wrangler or best mathematician of his class. He fancied that he would study as a lawyer, and he joined the faculty of St. John's College at the university until he was called home by his father in 1816 to assist in making the final observations for the great catalogue William and Caroline had been working on for all of those years. He would help bring that work to completion and then would extend it substantially by traveling a little bit later in his life to South Africa to make similarly detailed observations there. He would also do a good bit of work on chemistry, and his experience there would help him create the processes and tools that would lead to the development of photography, a term he helped coin. He also did extensive work in botany where, with his wife, the two would document and catalog over 130 species of the flora and the Cape of Good Hope. He also corresponded in great detail with Charles Lyell on subjects related to the fledgling science of geology. In 1831, John would publish what would become one of the most important books of the time about the nature and process of scientific inquiry. This work would become particularly influential at Cambridge, where it inspired many, including Charles Darwin, to pursue careers in the sciences. In 1864, he would publish the General Catalogue of Nebulae and Clusters, bringing to completion the work of his father and aunt, and also adding his own southern observations. What's really interesting when you look at the life of John is just how many different fields and areas his interest and his intellect touched. For someone who probably started off being thought of as either a child with a silver spoon born in his mouth or somebody who would just be handed a bunch of things in his life because of the work of his father, what you see in John is that same mentality towards careful observation, diligent work, and a sense of responsibility to do the job right. He and his wife Margaret would have 12 children, 3 of whom would go on to have significant and consequential careers in the sciences. Therefore, over the period from about 1778 to 1921, there was somebody by the name of Herschel making discoveries in one or more fields of scientific inquiry. What I think is most remarkable about all of this, when I sort of back up and I look at the whole scope of the thing, is that it all starts when a young man, still a teenager, fled a war in Hanover in 1758 and began a new life in England. While not completely a rags to riches story, what stands out to me is that beginning with William and Caroline, there was a dedication to hard work, careful data taking, and meticulous documentation. I think one of the common misconceptions among many who look at the sciences is that you have to be absolutely brilliant to do it. If you're not an Einstein or a Heisenberg or a Hawking or somebody like that, you just won't make that much of a difference. What I think we see here, though, is that the Herschels, whichever generation of the dynasty you might choose to examine, make their name through hard work. It was a similar thing when we looked at Marie Curie and her daughter and her family. Same idea. Sure, they're smart and clever and creative, especially that last one in William's case. But more than that, they're willing to get out and do these oftentimes mundane and monotonous work of gathering data day in and day out in order to understand the phenomenon they seek to inquire about. Moreover, what we see here is that their work is tremendously foundational. Everything gets built on top of it because they take those techniques of natural history, of documenting and cataloging all of the smallest differences in order to find this great compendium of knowledge. And as such, therefore, it will be their work that generations of other scientists will build their careers in astronomy on. So here's to the Herschels and to the legacy they'd bequeathed. If you have a glass, now's the time to raise it. As we wrap up this short scientific biography, let me be sure to note my sources. My primary source has been Michael Hoskins' Discoverers of the Universe. It's a good introduction to the lives and work of William and Caroline, as well as a brief discussion of the work of John. but I would caution the prospective reader that it bounces around a bit more than I care for, and the ebook version has some really distracting formatting issues. So I think it's a worthwhile source, I really do, but just be prepared to know that there's probably going to be some stuff in there that throws you off a little bit. And you have to maybe want to have like the Wikipedia article on whoever you're reading about up so that you can kind of place the stories and the narrative in that broader framework. I'd also like to once again acknowledge Tony Christie and Todd Timberlake's work that has gone into this episode. In the way of a few administrative notes, last week it seems that we've had a huge number of folks from the Australian province of New South Wales discover the show. If my download numbers are right, it seems like we may have added about 400 Aussies to the crew in the last week. If that's true, I'd like to welcome all of you from the Antipodes to the Odyssey. If you haven't already done so, come and like our Facebook page and leave us a note to say hello. Also, would one of you mind telling me how so many of you found out about the show? I'm just really curious why 400 people show up in a week. I think it's really cool, but it's also a bit of a mystery that I'd love to have solved. If you haven't done so, and this applies to everybody out there, be sure to subscribe to the podcast on whatever service you'd like to use. And if you have a few minutes, leave us a review. Also, if you enjoy the music for the podcast, go out and check out the new website of the Blue Dot Sessions at sessions.blue. Next week, we'll get back to the narrative and do what I think will be our final episode on the astronomy of the solar system before we travel outward with William Herschel into the reaches of deep space to see what that can teach us. Until then, full sails on your journey.